This week, we're talking about two different algorithms that are commonly used in machine learning for both classification and regression models. So one is extra trees algorithm, and the other is the k-nearest neighbors algorithm. So both of these algorithms are actually not even closely related. Extra trees is sort of an extension of what we talked about 2 weeks ago with random forest and sorry, 3 weeks ago, right? Or before we left for winter break, we talked about decision trees and random forest, right? And last week or 2 weeks ago, we talked about SVMs. So we're sort of continuing to talk about the idea of random forest and putting together these bunch of decision trees to create a more kind of accurate and stable algorithm. So I just kind of want to start off today by just talking about the extra trees algorithm and how it's similar and different to random forest and why it exists and why it's used. And then for the rest of the time, we'll talk about unsupervised learning and the k-nearest neighbors algorithm, and then we'll end off with sort of a code block that implements the k-nearest neighbors algorithm, and we'll have a few exercises for you guys to implement your own versions of the k-nearest neighbors algorithm for a few exercise problems. All right, so let's get into it. So first off, the random forest and extra trees algorithm are very similar. So if you guys remember, we talked about random forest. We start off with this idea of a decision tree where we can sort of have this logical breakdown of features to come to an eventual conclusion on what sort of dependence those features tell us, right? Or what sort of relationship those features have that allows us to draw a conclusion. And we're able to do that sort of visually with the decision tree and sort of splitting off based on a series of sort of simplified version if and else statements, right? So the random forest algorithm is basically just combining a bunch of these decision trees by basically sampling, or what's called bootstrapping, different parts of the data set, which basically means, so say you have 10 decision trees in your random forest algorithm, right? That means each of those 10 would kind of sample a tenth of the data set, and this sampling is with replacement, and basically it samples that and it calculates the optimal splits for each of the decision trees based off just that tenth of the data set that each of those decision trees can see. And at the end, the random forest algorithm basically averages or sort of puts together the results from all these different decision trees and what they came up with to come to a final kind of classification or regression scheme for your problem. So extra trees differs from random forest sort of two big ways. So the first is while random forest uses bootstrapping to sort of sample the data set, which basically means is that each decision tree only uses a part of the data set. The extra trees algorithm, each decision tree in it actually uses the whole data set. So what are the implications of this? Well, the first is that you sort of won't be able to eliminate as much of the bias as you do in random forest. What I mean by that is, say you have a data set that has a portion that's sampled by a single decision tree in the random forest algorithm is very biased, which means that it's not representative of the rest of the data set or the data in real life, whatever data you're collecting, right? So essentially, with a random forest algorithm, the decision tree that would be created from that would be a lot more biased than the one that's created by the extra trees classifier. So that's sort of one benefit of the extra trees classifier or regression model. So that's the one of the big points. The second big point is how they select the cutting points or the splitting points on each of the decision trees themselves. So if you guys remember, in random forest, there was this kind of measure of impurity that we calculated, right? So or we sort of calculated a measure to objectively identify which features to sort of split on as you move down the decision tree. So with the random forest algorithm, we had a methodical, objective sort of method to calculate the optimal split, right? But extra trees actually randomly select these splits without actually doing any computation. And you might be wondering why is that good, right? We obviously want to calculate and figure out the optimal one rather than just randomly sort of choosing a split. Well, the sort of benefit that you get is actually, before I talk about that, both actually optimize after the split. What I mean by that is once you make that split in that decision in each of those decision trees for each of the algorithms, then the split points that are then selected still have to be optimized to get the minimum number of features that can still classify or produce the output that you want, right? So essentially, there's still some optimization that happens after the split with both algorithms. The only main difference is that before the split happens, when you're choosing the splits with random forest, those splits are chosen by an objective sort of index, which is either that Gini impurity index, the entropy calculation that we did. If you remember those stuff from a few weeks back. If you don't, you can always go look at the notebooks. Remember, they're always in the drive. And for extra trees, it randomly selects that. So the benefit from that is that the extra trees like either regression model or classification model that you can create from the extra trees algorithm is going to be a lot faster than the random forest algorithm on average, just because of the fact that you don't have to spend the time computing the optimal split. And in fact, in some cases, that element of randomization that the extra trees classifier allows you to have in it might actually produce some results that are more optimal than what can be produced by a random forest algorithm. So essentially, there's sort of three main parameters that you sort of have to specify in both the extra trees and random forest algorithms, which are the number of decision trees you want in your algorithm, the number of input features to select, whether that be randomly selecting them or optimally selecting them through some sort of methodology. And then the third thing would be the minimum number of samples required to create a new split point. So as we talked about earlier, the higher you make the minimum number of samples required to basically split, will basically allow you to have a more simplistic algorithm, right? Because you have less split points if you have increase in minimum number of samples required to make a split. So no, Arul, I'm not sharing my screen. I'm just talking about this right now. I don't have a PowerPoint for what I'm talking about right now, but for the k-nearest neighbors algorithm, I do have a PowerPoint. Just if anything I'm saying doesn't make sense, just ask me. I'm happy to answer anything. But essentially, the summary of what I talked about the last like 5 minutes is the extra trees algorithm is very, very similar to the random forest algorithm. It just sort of marginally improves upon it by looking at the entire data set, the entire sample of data you have in that training data set in each of the decision trees, while random forest sort of uses something called bootstrapping, where it samples parts of that training data set. And so the benefit of sampling the entire data set for each of the decision trees is that there's sort of a little bit less bias in each individual decision tree in that forest, which possibly could lead to some improvement in your algorithm by using extra trees over random forest. The second major thing is extra trees randomly select the splitting points in each of the decision trees, which allows for this sort of implementation of randomization into your algorithm, which can sometimes produce better results. So those are the main differences. So that's kind of sort of what you should be considering when choosing whether to use a random forest algorithm or the extra trees algorithm. And extra trees is also available through the same scikit-learn package or library that we've been working with. Remember, most of the algorithms we're going to be talking about throughout the rest of this semester are all going to be through that scikit-learn library. But when you start to get more advanced and start to implement your own versions of these algorithms, you sometimes will be using frameworks that are outside of Keras and scikit-learn. So these are just sort of simplified versions of a lot of things that you'll be looking at later, probably in college, if you major in CS and take a lot of AI classes. All right, so that's all I want to talk about with that. Any questions about extra trees and random forest? No questions? All right, then let's get into Sam. By the way, you're recording, right? Okay, cool. So let's get into the kind of this discussion today, or the presentation today, which will be on k-nearest neighbors. All right, so let me quickly share my screen, and then we'll get into this. All right, so everyone can see my screen, right?
Yes.
Yes, all right. So this is the same, if you remember, we talked about, I think SVMs, I use the same, the PowerPoint made by the same person at Cornell, just because I think her PowerPoints in general are really easy and simple to understand. Even though sometimes there's some higher level math in them, I still think they're really simplistic, and the diagrams she has are good. So let's get started with this. So basically, when we talked about machine learning, right, way back when, we sort of broke up this idea of learning, right, into two components, right? We said that there's sort of two methods of learning. The first is this supervised algorithm, supervised learning, which is based around the fact that you know what the output for a bunch of different training samples is, and you're basically having a bunch of features that you can then use to predict that output, right? So that's what supervised learning is. And we have unsupervised learning, where we know what variables or features we have, and we know we know the different possible outputs, but we don't explicitly have the data, or what's called labeled, which basically means we don't have an associated output for each of the inputs that we have, right? So we don't have those sort of labeled outputs for each of those features. So essentially, we somehow still need to be able to create an algorithm which will allow us to analyze the relationship between the features and create something that can sort of predict the output of new data. Well, that whole class of machine learning is called unsupervised learning. And then, of course, there's this third class, which is sort of in between it, where you have a little bit of data that's labeled, but most of it's not. So therefore, you get what's sort of called semi-supervised learning, which is it's actually a field that's getting bigger nowadays. A lot more research in that area. But anyway, so going back to this, so we're going to be looking at something called instance-based learning. So this is essentially a fancy way of saying, look, we don't know what the outputs are for the set of features that we have, right? So if you're working for a certain problem that has maybe 10 different what we call independent variables, right? So 10 different variables that could predict that dependent variable, but we don't know what the specific output or dependent variable, the value of that dependent variable for each of our samples in the training data set. So therefore, we use something called instance-based learning, where we basically take up on the idea that similar examples or similar inputs in our training data set will have similar labels or similar outputs. And we basically just classify new examples like similar training examples. So the algorithm, essentially the algorithm for k-nearest neighbors is given some sample X for which we need to predict its class Y. Class is just a fancy way of saying for classification is what class in the hierarchy of classes. So like, for example, maybe the output you're trying to predict is what grade someone is in, and you're trying to use a bunch of different variables, such as like, I don't know, what their interests are and where they what they do in their free time to figure out what grade they're in. And so in that case, the different classes, for example, in high school would be 9th, 10th, 11th, 12th. And if you're working with the regression algorithm, the output would be the specific numerical value for that sample. And then you basically will find the most similar training examples to that sample. So basically, you're going to be looking through the rest of the data. So unlike supervised learning, where you basically, a lot of these supervised learning algorithms we've looked at especially, where we sort of treat each of those samples in the training data set as sort of independent, and we don't use the values of other training samples to base a judgment on the sample we're looking at. We actually have to do that here because we don't have that sort of output reference for each training value or each sample or each data point in the training data set. So The questions are basically at this point, right? So if we're given this algorithm, we find the most similar training examples, and then classify x is just some number, right? So that could be like 5, 10. We classify this example like the most similar examples we see in a training data set. So essentially, what we're doing here, right, is we're basically just sort of clustering the different training examples to the groups, right? Does that make sense? Because the algorithm essentially what we're doing is we're looking through the data set that we have, or the training data set, and finding which samples or which data points are similar to each other. And then we're sort of putting them together into their own class. If it's a classification algorithm, or if it's regression, we're sort of clustering them around a certain numerical or numerical point. And so the questions are, how do we determine similarity? How many similar training examples do we consider? And how do we resolve like inconsistencies or biases among the training examples, right? So these are 3 big questions based on the algorithm we proposed here, right? So how do we sort of figure out these 3 things to sort of implement this algorithm? Well, so the idea of k nearest neighbors algorithm essentially stems from the fact that k in the front of it can be any number, right? So we can implement a 1 nearest neighbor algorithm. And essentially what that is if you go back here, I don't think I can play the animation. There's a cool animation here, but essentially, say we have these points that are on the outside, right? So this point, this point, this point, this one, this one, this one, as other training examples, right? And then we have this one in the middle as also being red, right? So we have these sort of 7 points, and then there's this new point or new point that's sort of brought in, and we want to figure out whether it's going to be red or it's going to be green. So basically what the k nearest neighbor algorithm says is, let's look at the k nearest neighbors to that point, and then based on what sort of class they're in or what their numerical value is, let's sort of take a weighted average of those to come up with our final label or final class. So essentially, if you look at this example, what we're doing k nearest neighbors algorithm with 1 neighbor, right? So we just look for the closest neighbor or closest point, right? So from this black point, the closest point is this red point. So therefore, this algorithm would say, okay, let's make this point have the same, I guess, output or the same class as these other red ones, because its closest neighbor is another red dot. So we label this as red. So yeah.
I have a question about the previous slide.
Yeah.
So all the points are being plotted, but they're like based on multiple factors, right? A lot of different parameters, right? So is it like something similar to what we learned in like some of the previous lessons of like how to plot a point with multiple factors? Is it like
exactly. So Arul, I think that's a very interesting, very good point, because a lot of people are wondering, if we have so many features, right, how do we visualize these points on a plane? Well, right now these points are plotted in 2D, right, which means that we could have up to 2 variables that sort of make these points. They're sort of 2 separate independent variables or features that when you plot them together, so you plot one variable on the x-axis and one on the y-axis, when you plot those, you can end up with sort of this 2D graph where you then could plot each a point which represents each of the training instances, right? So when we work with an actual machine learning algorithm, we're essentially just increasing that feature space. And when I say the word feature space, I just mean increasing the dimension of what we have, right? So if we have 3 variables, we look at it in 3D, and of course we can draw 3D. But once you go to like 4D, 5D, and you start to get more and more features, these algorithms still work in the same fashion, but we just can't visually represent how they work very well, right? Because we can't draw like 4D shapes. Does that make sense?
Yeah, that makes sense.
Yeah. So like we talked about before, like Arul brought up, essentially we're just looking at these different points, and in all the examples we're looking at, we're just assuming they're 2 independent features that we're using to predict an output. But in real life, when you're working with real data, you might be using a lot more features, and in that case, these algorithms still work in a similar fashion, but we just can't visually represent them well. All right, let's move on to the next slide. So This is not an important detail, so I'm just gonna skip this slide. Now you might be wondering, how do we basically come up with this sort of similarity index? Well, if we stick with this idea of graphing the points, right? So say we have two independent features that we're using to predict an output, right? So we plot them on the x and y axis, put one on the x-axis, one on the y-axis, make a little graph, right? So essentially, how do we create a sort of a similarity index between these two? So how do we figure out which points are the most similar? Well, the sort of naive or simple solution would just be to figure out the distances from one point to the next, which is essentially how the k-nearest neighbor algorithm works. We basically use what's called a Euclidean distance metric, which is just a simple formula we learned in Algebra 1 when we're calculating the distance between points, right? Like a line or something. We use this formula, right? We use distance of a and b equals the square root of a1 minus b1 squared plus a2 minus b2 squared, right? And then we can also extend this distance metric to multivariate data, which basically means more than 2 dimensions. So essentially what you do is you take the square root of the sum of each of these sort of differences. So in 2 dimensions, we only had an a1 and a b1, right? But I'm sorry, we had an a1, b1, and then a2, b2. We have 2 points, right? But in 3 dimensions, we have an a1, a2, a3, and then maybe a b1, b2, b3, because we have 3-dimensional points. And we can keep extending upon that. So the Euclidean distance metric will just be the sigma, or the sum of all of these different a sub i's and b sub i's. So this is sort of the metric or the similarity index that will be calculated. We'll just be using the sort of distance metric. And that logically makes sense, right? So this is not a very complex concept, even though the math might look a little complex to some people. But yeah, it's just what it seems like it is. You're just looking at the distance between the point that you sort of are trying to classify or find the value of the regression model, and the closest point, and you're using a distance metric to find that. So with the one nearest neighbor algorithm, we're only looking for one neighbor, and if we're trying to figure out how to fit it with the local points, we're just going to predict the same output as the nearest neighbor. So you guys now might be wondering, okay, so essentially what we've done is we're basically using every single training example and sort of making our judgment on them, so sort of classifying them or finding their regression value through looking at all the other samples, right? So you guys might be wondering, what's then we actually don't have any concrete method of accounting for bias, right? Because all our sort of assumptions are based on the idea that the actual distribution of those features that we've been looking at in our training data set is actually what it looks like in real life, right? Like in the testing data set and in whatever real world application our algorithm has. And oftentimes, as you guys know, data is biased. So when it comes to that point, the k-nearest neighbor algorithms is very bad at sort of making those sort of extrapolations. It's only good if the data you're trying to predict looks very similar to the data you already have. And like I said, most of the time that doesn't happen. So this is why this is a very, very naive and sort of basic unsupervised, probably the most basic unsupervised learning algorithm. So now let's extend this one nearest neighbor algorithm to multiple, so k nearest neighbors. So when k equals 3, so we were looking for the 3 nearest neighbors to a point. In this situation, right, if we start off with this point, the 3 nearest neighbors, which we established by that Euclidean distance metric we talked about, would be this point right here, this point right here, and this one right here. So in this case, 2 of them are red and 1 of them is green. So since we're looking at a classification problem, we use what's called majority voting, which is essentially figuring out out of these 3 points, which class is the majority. And in this case, it's the red because 2 out of 3 points are red. Well, here, when it's k equals 7, right, we look for the 7 nearest neighbors, and in them, 1, 2, 3 are green and 1, 2, 3 are red. Well, in this case, since it's a tie, the algorithm would basically assign it a red and a green value. it wouldn't say, okay, let's have some other metric to sort of break the tie. It just doesn't break ties because it's not that sophisticated. The k-nearest neighbor algorithm would sort of apply the class label of both the first class and the other class. So in this case, this is representing it by colors. If you mix red and green, you end up with blue. That's why like you end up with this. You label it blue. All right. So now let's look at an example. So we sort of have these 5 different variables, right? As sort of our independent variables, and then our dependent variable is will we give a big tip. So the food is great, the sort of chat or the sort of service is good, and if you were hungry or if you were fasting, and if the price was high, normal, or low,
I think
and if there was,
I'm
yes.
pretty sure the fast means like how fast was the food delivered to you?
Oh, maybe, yeah. Wait, that probably makes a lot more sense, I guess. But the actual, by the way, just for saying, the actual interpretation of the variables themselves won't mean much to us, right? The way we sort of apply these sort of variable names to these different features is just for the humans to understand them. The algorithm only sees the feature spaces of each of these features. It doesn't actually see the name. So like Victor's probably right, where fast is how fast the food is brought to you. But in the end, if you thought, like what I thought, that it was how hungry you were when you were going in, it actually wouldn't change how you approach this problem. Just something I want to add. But yeah, so let's say fast is how fast the food was. In this situation, if we have another training example, which is the food is great, the sort of service is not that good. The food is not fast, the price is normal, and there is no bar. Would you give them a big tip or not? So we use the same Euclidean distance metric to figure out and first of all, k equals 2. So looking for the 2 closest neighbors. So in this case, since everything is sort of ordinal, right? We have these different categories. We don't have a sort of continuous distribution of these variables. We just essentially look for a similarity comparison. We just look for which of these samples is the most similar, so which has the most matches among each of these different features. So the most similar would be number 2 because it has 4 matches and 1 mismatch. The only mismatch is how fast the food was there, right? So in this example, it was fast, and in this example, it was not fast. And the second most similar would be number 1, which has 3 matches and 2 mismatches. So essentially, since both of these had yes as their output, then we would sort of have this new example is yes. But then you guys now might be wondering, wait, I thought we didn't have what the actual outputs of the big tip were, right? Because when we talked about unsupervised learning algorithms, we don't know what the output variable is, the dependent variable, the value of it. But in this example, in that chart, we knew the output. So how exactly is this still unsupervised? Well, essentially, a lot of unsupervised learning problems suffer from what's called the cold start problem, which is essentially when you have very little amounts of data, right? You need to sort of manually go in, and after the sort of clustering has happened, you need to identify what those numerical like labels or classes translate to in sort of an output. So in this case, when this clustering happens, we sort of get the results for all these different training samples, right? And instead of having like a big tip as being yes or no, we'd have maybe zeros and ones to represent the different classes that they're clustered into, and would essentially have to go in and be like, okay, well, 0 corresponds to yes, and then 1 corresponds to no, as in whether you left a big tip or not. So yeah, that's kind of how this works. So with the second example, we had we do the same thing again, right? Where the most similar example is a no, but the second most similar example is a yes. So therefore, the similarity metric for this would be a yes/no, which in terms of class would probably output something like 0.5 instead of 0 or 1. All right. So now let's talk about a few sort of hyperparameter issues and see how do we choose these different hyperparameters for our k-nearest neighbors algorithm. Well, essentially, the three big things, or sorry, the two big things actually. The first is selecting the number of neighbors we want, and the second is identifying how to weight the different features that we have. Right, so there's sort of two big problems that we'll talk about. So the first is how do we select the number of neighbors we want to use? Well, if we increase, so the advantage of increasing the number of neighbors is that our algorithm will be less sensitive to noise, right? Because say you have, say this the training sample that you have that you're looking at, for some reason is plotted or is very next to an outlier from the other class, right? Well, if you have a very small k, maybe it's even 1, you'll classify that new point incorrectly, or that new training data point incorrectly. So to kind of avoid that from happening, you want to increase k to sort of encompass more neighbors and sort of decrease the variability or the variance of your algorithm, which will make it less sensitive to noise. And if you decrease in k, it allows you to capture the finer structure of space. Essentially, what this means is you'll sort of get a better understanding, or your algorithm will get a better understanding of how the data sort of boundaries are shaped, right? Because if you make k very large, right, each example that you're looking at, or each new example, will sort of encompass a lot of the other training examples, right? Because if k is something like 20 or 25, where it's like huge numbers, and you only have like maybe like 50 to 100 different samples, a lot of samples in both classes will be encompassed in the calculation, or will be considered in the calculation of the class of that new point. So if you make k too large, then you'll end up with the issue of not being able to understand the kind of feature space or space very well. So you obviously want to make sure k is at a good number. You don't want to make it too large or too small. But of course, this depends on the type of data you're working with, right? Logically, if you're working with a very small data set, you want to make k a little bit smaller, right? Because if it's too large, too many of the samples that are in your training data set will be considered when you're trying to add a new point or figure out the class of a new point in your data set. So you want to sort of balance the value of k. Lastly, we'll talk about the recursive dimensionality, which is something I already mentioned. Sort of actually didn't explicitly mention, but sort of hinted on, which is essentially that when you add a lot of attributes, right, the prediction accuracy actually will go down very quickly. And the reason why is irrelevant attributes can easily kind of swamp information from relevant attributes, which basically means that the algorithm won't know that one variable or attribute is more important than another, right? Because why should it? You haven't told it to be, you haven't weighted the attributes or told the algorithm to consider them differently. So it'll consider the irrelevant ones and the relevant ones as sort of the same. And when this happens, the similarity/distance measure becomes very unreliable, right? Because the irrelevant attribute may cause some outlier, or some not even outliers, just some point from another class, for some reason be very close to a point or data point from another class. So the sort of solution to that is feature engineering or pre-processing, where you sort of only select the most important features through other methods, so other algorithms that are outside of KNN, and then apply a k-nearest neighbors algorithm afterwards. Or you can weight the attributes differently, or you can even increase k slightly so that you sort of decrease a little bit of that bias that happens when you when this distance measure becomes a little bit less reliable. So these are sort of three remedies to that. And lastly, let's quickly talk about a few of the advantages and disadvantages of the k-nearest neighbors algorithm. Well, so the first disadvantage, I guess, is you need to have a similarity in distance measure and attributes that match whatever target function you're looking for. So this just means a fancy way of just saying that the data that you have and the attributes or features in it need to accurately reflect what the question or the output of that data is. So if you have too many irrelevant attributes, the KNN will be very confused and your outputs and results will be really bad. So you need to be sure that the attributes or features that you're putting into the KNN are relevant and actually are significant in figuring out what class that data point is in. And then for large training data sets, you must make a pass-through data set for each classification, and this can be very time-consuming and computationally expensive for large data sets, which is why KNN is usually something that's used by beginners, and it's sort of a more simple to implement algorithm that requires little tuning, and is often done on smaller samples of data rather than a whole and huge big data set. So yeah, that's a quick introduction to KNNs. Does anyone have any questions about the theory behind it before we look into some implementation stuff? Nope.
Sanjay?
Yes.
I have a question.
Yes.
How does increasing K make it less reliable?
How does increasing K make it less reliable?
Less sensitive to noise.
Oh yeah, okay, that's a great question. Well, essentially, so if you've taken stats, or if you maybe, I don't know if you've taken stats, but essentially the reason why is when you have smaller amounts of data, in general, what's the standard deviation or the variance, which is basically how variable the data is for these different features, is often going to be larger, just generally on average. So when you have larger amounts of samples, larger amount of sampling data, that sort of variance is decreased. And in machine learning, the goal of literally all algorithms is sort of standardize your inputs and make sure that variance or standard deviation is low, because in general, a high variance causes high bias in data. When you have a highly biased algorithm, your outputs on independent testing sets and real life data is going to be a lot worse than if the algorithm's not biased. And this is also why you can go into some like social sort of classes in college, which talk about the intersection of tech and society. And you'll hear a lot about how some of these algorithms that we use in our everyday life are like biased just because the training data that they're trained on are biased. So sometimes you'll hear about like these facial recognition algorithms that, like don't work so well for people of color just because the training data was full of old white males. So yeah, that's essentially why increasing the amount of samples or increasing K helps to do that, because you're basically considering the features of more of the training samples for that to basically come up with the class of that new training sample you're putting in or considering. Does it make sense?
Yes, thank you.
All right. Okay. So let me pull up this now. Okay, so now we look at a quick sort of Google Colab that we're looking at that will sort of basically go over K-nearest neighbors. Well, so introduction. So if you guys know about the Google Science Fair, it's now been discontinued, but it was a very big thing back in the early 2010s, so about 2011 to 2015. A lot of high schoolers participated in this competition, and in 2012, AI and machine learning was still a field that wasn't being really explored at the rate that it is being now. Just because a lot of the technological advances and frameworks that we have today just didn't exist then. So for her, so back in 2012, she built an algorithm that determines whether patients have breast cancer based on attributes in a biopsy of breast tissue. And her attribute classifier based on a neural network, which is something we'll talk about, was 97% accurate with a 99.1 sensitivity to malignancy. So this basically just means that our algorithm was very good and it was able to do a job very well. And while today making an algorithm like this is very simple, just because of all the frameworks that we have and all the sort of things that we already have working for us, back in 2012, this is a very big thing to do. So basically, we're going to be doing the same. We're going to be using a K-nearest neighbors algorithm on the same data that she used for her neural network and seeing how we do. So let's first read in the data. So she basically took in clump thickness, the uniformity of the cell size, the uniformity of the cell shape in breast cancer, the marginal adhesion, the single epithelial cell size, the barrier nuclei, the bland chromatin, what type of chromatin was there, whether there was normal nucleoli, and then mitosis, and then finally what the diagnosis / output class was. So basically, usually when you're working with problems that involve machine learning, it's very helpful to understand what the significance of different features is, right? Because right now I can't tell you what 5 on marginal adhesion means. I just don't know, because I have to go take a look at it and understand what the different classes for a marginal adhesion represent. So it's often useful to kind of get a better understanding of that before just sort of blindly going into a problem and trying to implement an algorithm. But anyway, since it's too much work for us to figure out what each of these means, we will sort of just take a very naive approach to this and just assume that based on the data, the k-nearest neighborhood algorithm seems very good for this. So first thing we do is we're going to make a plot, and that plot is basically going to hold the clump thickness on the x-axis, and on the y-axis the uniformity of cell size. And we're going to plot this with blue representing what sort of color we're looking at, right? So if we have something that has low clump thickness and low uniformity of cell size, it's more likely to be blue than if something has high clump thickness and high uniformity of cell size. And I'm assuming, based on how they map these, that 0 represents something that's not malignant, something that's benign, which basically means a tumor that isn't going to spread around your body. And 1 is something that's malignant, which is something that is going to spread around your body. So if we have this, right, and we pull out that k-nearest neighbors algorithm that we're looking at, and say we have this new point right here, right, and say we say k equals, I don't know, 3, right? What will this point here be, blue or red? What do you guys think? So we have this point in right here in the middle, which is black. Will that point be attributed to the red class or the blue class, based on if k equals 3?
Red.
Yeah, it'll be attributed to the red class. So we're going to assume that someone who has a clump thickness, just looking at these two features, someone has a clump thickness of 6 and uniformity of cell size of 7, they likely will have a malignant tumor. So yeah, not hard to guess the tumor is probably malignant. But now let's basically implement the k-nearest neighbors algorithm. So first thing we're going to do is we're just going to basically, going back to the skills we learned with pandas a while back, we're first going to be pulling out just these 2 variables, right? We're just going to use these 2 features, and we're only going to be predicting. We're going to see if we can predict the accuracy of, if we can predict whether a tumor is malignant or benign just using clump thickness and uniformity of cell size. So first thing we're going to do is we're going to create the training and testing data. We're going to create the training data for the features and then the sort of dependent variable with the training data for that. And then we're going to normalize the different features that we have by just taking the individual values of them, subtracting them from the mean, and then dividing them by the standard deviation. So this is sort of a standard way of what's called normalization of data. So on that, and now let's create a series, which is something we talked about earlier, for the new breast mass. And we'll basically scale it in the exact same way we scaled this training data set. So now let's calculate the Euclidean distance between the new mass and each mass in the training data set and sort the distances from smallest to largest. So we're basically going to use NumPy to do that. Remember, NumPy can perform operations on entire lists of data rather than just doing it on a single number. So we're going to use that to create a sorted list of information. And as you can see, so for this new mass that we just created, right, which is sort of this like equivalent of this new black point that we have, right, we calculated distances from all these different features, and we see that it's very similar to entry number 3, 225, 304, 452, and 499. And now let's kind of sort these 10 entries So yeah, we sorted them, and now let's take the first 10 of them, which is what this does. And now let's look up these indices, right? Because these are just indices from this original data that we had up here. So we want to grab just those indices and make a new data frame with those, right? And so we just have these 10, and we see that out of them, most of them are going to be malignant, right? So therefore, our value that we create from here shows that 8 of them are eight of those closest 10 neighbors are malignant, and 2 of them are benign, which then means we can probably say with an 80% probability that this new tumor that we saw right here is going to be malignant. So basically, that's the gist or the implementation of the k-nearest neighbors algorithm. And we did it manually here, right? We manually calculated the distance, and then we manually scaled it. But when we use scikit-learn, we can do it very easily and do it in less than 10 lines of code. So we're basically going to use this pipeline, essentially, which is just a fancy way of encompassing the k-nearest neighbors classifier in a single in like a very concise and easy to run as a code block. So because basically scikit-learn has made this make pipeline function that allows us to define a pipeline rather than having to manually go through and do these calculations. So we run all of this and we fit the pipeline to the training data set, and now we're predicting the test data set. So if you look at the predicted probability, we see exactly what we saw up here, right? So instead of having to manually type out all this code and manually scale it and then calculate the Euclidean distance, we can just do that with this k-nearest neighbors classifier from the sklearn.neighbors library. So that's how we can do this, and this is sort of just a brief introduction into the k-nearest neighbors algorithm. So now we have these 2 different exercises at the bottom, right? So I want everyone right now to go to the Google Drive, which is the shared Google Drive on the CHS Computer Science Club website, or sorry, Facebook. It's on Facebook, right? Victor, where is it at? Is it on the Facebook? It's on the Facebook, I think. Yeah. So that everyone can open that. It's called the Machine Learning Subclub. That's the title of that Google folders. If you go to week 9, you'll see that the same notebook that I'm looking at has already been put into there. So now I want you guys to try to do exercises number 1 and number 2. And essentially, they're virtually the same as the example we just went through, but just for you guys to get a feel for the code and sort of understand what to do. So numbers 1 and 2, and that's going to be your homework for this week, and we'll check it at the beginning of next class. All right. Any questions before we're done for today? So today's a little bit shorter class, only about 50 minutes.